That title itself somehow provoked a kind of nostalgia and great feeling in me, because about 2 decades back in the year 2000, the Educational Foundation in Northeast, Holy Cross, took up an activity or an effort what we called named as NESNIM, acronym for Northeastern Students National Integration Movement. And it is still continues. It got evolved into various activities and programs, but we were able to bring students from number of schools and colleges from all over the Northeast, physically bringing them together for 3-4 days for cultural, socio-cultural, and intellectual exchange and programs activities. It had been very huge success. Since we are doing it physically, it took a lot of effort, energy, resource, everything, but it was something very great. Now that we have the virtual facilities, online gatherings, it is much easier, yet we are able to connect across the globe and world. So this is all the more exciting. With the short time and maybe energy and expense, we are able to come together, share our culture, talents, gifts, knowledge, and time together. So I'm very much excited, and I see great scope in taking ahead as you have proposed various activities and programs in the coming days. And on behalf of uh, Holy Cross College Agartala, and especially Dr. Reba Chakravarti, the HOD of Zoology Department, and Dr. Pankaj Chakravarti, Coordinator and Academic Dean and Coordinator IQAC, and all of us here at college, we congratulate you, and we are very grateful for your generous offer and your such an exemplary activities, and we want to learn a lot from your autonomous college. Is as I mentioned, a big sister, big brother for us. We wholeheartedly join hand with you and look forward to a great time together in learning, sharing, growing together. Thank you, one and all, and have a good day and good afternoon. Thank you.
Thank you, Father. It is really amazing, your words. We'll try to keep it, and we'll have wonderful programs ahead. So now I request Father Prashant, Principal, Sacred Heart College, Thevara, to speak a few words at this point.
Dear everyone, a warm namaskaram to all of you. I'm really happy and excited, as Father Benny rightly pointed out, to be on this platform with you all. It's really amazing to note that, in spite of the very odd and very adverse kind of circumstances, the technology has made it happen, made it possible for all of us to come together. And this is truly national integration. We have Northeast coming with Southwest, and we are Kerala in the southwestern tip of the country, and Northeast we have Agartala, and it is really wonderful that the cultures are getting united on this virtual platform, and technology is uniting us. But not only technology, before and beyond technology, there are human minds working behind that, and I really appreciate Dr. Pius to have taken this initiative, and the extended hand of welcome by our so-called younger sister of Holy Cross, Father Benny, and his wonderful team of Dr. Reba and Pankaj and all of them. And out here with us, our physics department taking the lead together with our internal quality assurance cell led by Dr. Johnson. And also our technical team, whom we name as Hearty and Beavers, who have been building the technology framework for all this. This is really a very great confluence, and really amazing that we have somebody from America. So this is not only North and South and East and West united, but also morning and evening getting united. So now it is morning in America, maybe very early morning, but Dr. Varghese is there, and again our former student and former faculty, my own neighbor, friend. We feel really good that Dr. Andrew has made it to this occasion, and definitely I hope that the gathering will benefit from his sharing. And I hope that this should be a real beginning, and we should go on exploring further possibilities of working together and enriching each other by that. Yes, there is a mix of institutions, a little old and the younger one. So the mix of young and youth coming together, forming a stronger bond, that is really good. We will mutually benefit from that. And I also hope that this will not confine to this virtual platform. We will definitely travel We will reach to each other. Our students and our faculty will travel to each other and share our culture and our learnings, and thus make the knowledge seeking community a richer and wiser. As our college motto goes, a righteous heart seeks after wisdom. May all these endeavors lead us to the real source of wisdom, God Almighty, and may the Sacred Heart of Jesus bless us all. I once again thank everyone who has worked behind this, especially Dr. Pius, who have taken initiative. Let the initiative sustain. And nice to see you, Father Benny, like this. You were very audible and very visible. Don't worry. In spite of the technological snag, you were very visible and very audible. Thank you. May God bless us all. I wish the gathering the very best.
Thank you, Father Prashant, for your inspiring and exciting words, and we love it. So now we just move on to our first event of this program, Ek Bharat, Shrestha Bharat. We have got our esteemed speaker, Dr. Varghese and Chirayath from United States. And I request the Department Secretary, Dr. Robi Chiriyan, to introduce the speaker.
Good evening, all. I am Dr. Robi Chirayath, Department Secretary of Physics, Sacred College, Kochi. Let me get in straight to my assigned task of welcoming Dr. Varghese Sando Chirayath. Dr. Varghese Sando did his bachelor's from Sacred Heart College, Tera, Kochi in the year 2002. He completed his post-graduation from Maharaja's College, Ernakulam. After obtaining PhD from Indira Gandhi Center for Atomic Research, Kalpakkam, he joined as assistant professor in the Department of Physics, Sacred Heart College in the year 2013. During his stay at Sacred Heart College as faculty, he served as a visiting summer researcher to the Qatar University for the years 2013 and 14. The research interest made him to move to Department of Physics, University of Texas, Arlington for his postdoctoral research during the period 2014 to 19. Since then, he has been associated with the University of Texas. Dr. Varghese Sando Chirayath is currently working as an assistant professor of research, Department of Physics, University of Texas, Arlington. During the Sacred Days, as student and teacher, he was very active member of the department with many physics association activities under his credit. I feel very happy when I recollect those days shared with Dr. Varghese at Sacred Heart College. In today's webinar titled Understanding Matter Using AntiMatter, Dr. Varghese Sando will briefly introduce few of the widely used positron spectroscopic techniques and will discuss recent experimental results from their lab to enrich young minds. With this short introduction, I welcome my dear friend Dr. Varghese Sando for this inaugural webinar. Thank you. Over to you, Dr. Varghese Sando.
Excuse me. So,
Hi.
can I speak? Talk will be around 40 to 45 minutes, after which we will take a few queries from the audience, I suppose. Thank you.
Thank you, Robbie, for the kind words. Please let me know if you have any trouble hearing me at any point of the seminar or webinar. Let me first thank the organizers of this webinar for inviting me to give this first talk. It's really humbling to hear the nice words from Father Prashant and all the staff at Department of Physics of Sacred Heart College. I'm also thankful to the principal and staff of Holy Cross College for welcoming me with open hands, and especially all the participants who have joined to hear me talk. My special thanks to Robbie Chirayath, my dear friend, colleague, for just suggesting my name for this talk. And so, without any further delay, let me go into the talk here. So I'll start sharing. If you have any trouble seeing it, please let me know. So presently, I don't seem to have access to share the content. Should I be made the host or something like that to do that?
So I think we'll see that. I will make right now.
Okay.
This is later. So Varghese, you can start speaking. So in the meantime, I will make that one.
Okay. So today the topic would be to. My purpose is to introduce a technique, positron annihilation spectroscopy, which is widely known, but yet it's not as deeply entrenched in the research community as it should be. And hopefully, with this talk, I would be able to excite some of the minds here to pursue research in the field of material science, and at the same time take up positron spectroscopy as one of the tools to understand the nature of matter. Now, as the talk, the title of the talk goes, you're trying to understand matter using antimatter. That itself is it's very interesting. One of the advantages of using an antimatter is that you don't have very much antimatter in the universe, right?
Varghese, excuse me, you have been made the presenter.
Okay. I think I can. Yeah, now I can share the. I'm able to share it. Thank you. So are you able to see it?
Yes.
Okay, thank you. Yeah, so as the title goes, we are trying to understand matter using antimatter. So let me start off with introducing the members of my lab here. Dr. Alex Weiss, and Dr. Ali Koyman are the supervisors of this lab. And then I'm joined in the lab by Dr. Randall Gladen, who was a previous student. He graduated last year, and he is presently working as a postdoctoral scholar with us. Another graduate student, Dr. Alex Fairchild, graduated just 2 weeks back. And we have Seema and Jack and Andy, our new students with us. And most of the work in this has been actually done by Randall and Alex, and I was just was part of it. And this work was supported by Wells Foundation of Texas and NSF grants by as shown here. Now, so usually people show the outline of the talk as the next slide, and then have points, like bulleted points as to what they would try to cover. Now, I did not want to do that most of the time, sorry, most of the time what happens is there is a the speaker would be able to go only till half the bulleted points, and it will be really embarrassing to see that he has not completed the talk. So what I've done is I've kept my outline abstract, literally the abstract of my talk.
No, don't tell. Participants are requested to keep the mic mute, please. Thank you.
Yeah. So the main thing we just need to focus here is this highlighted part, is that I'll try to introduce a few of the widely used positron spectroscopy techniques, and if time permits, I would show some of the recent results from our lab, which can reveal some electronic transitions which was not previously observed or could not be observed with other techniques. So when I speak to a lot of people are actually not aware that antimatter exists and it is real. So antimatter is real, and usually antimatter is the opposite particles of ordinary matter. And the antimatter that I am talking about is positron. It is the positive cousin of electron. And positron was discovered by Carl Anderson in 1932 while he was looking at his Wilson cloud chamber photographs, because he was studying cosmic ray showers, and he was looking at the cloud chamber photographs when he discovered a particle which behaves like a positive electron. And that's what he reported. That's the report shown here. And coincidentally, this is positron's birthday, because birthday month. The positron was discovered in August 2nd, 1932. It's like the positron is like 88 years old now. And it's really heartening to know that we have a direct academic lineage to Carl Anderson, because from Carl Anderson all the way back to Dr. Alex Weiss, they are connected through a PhD supervisor guide kind of relationship. Donald Glaser, who was a student of uh, 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 Carl Anderson, and Len Roylig was a student of Glaser. Carl Cantor was a student of Len Roylig, and Alex Weiss was a student of Carl Cantor. So we have a tradition going way all the way back to the discoverer of positron. And okay, so for some reason,
Yes, Dr. Varghese.
yeah, let me start back, because I okay, so we have an academic lineage all the way back to Carl Anderson. Carl Anderson won the Nobel Prize for the discovery of positron, and Donald Glaser actually won a Nobel Prize for the discovery of bubble gas chamber. Now, where do you find antimatter? You do not buy them from a store. In reality, where we get is we get our antimatter, that is positron, from the decay of a radioactive source, sodium 22. Sodium 22 decays via a positive beta decay into its daughter nucleus neon, and an electron and a positron neutrino. And so you can see that one of the protons of sodium decays into neutron and positron. The positron comes out of the material, and in addition, there is a neutrino emitted along with it. Now, after this decay process, neon is in an excited state, and so it goes into a de-excited state by the emission of a gamma ray. This gamma ray has an energy of 1.28 MeV, and this emission occurs within a few picoseconds from the emission of positrons. So the emission of gamma rays, 1.28 MeV gamma ray, signals the birth of positron. And in the background that I showed is the source module that we use in our lab. Now, what happens when a positron and electron meet? When a positron and electron meet, they annihilate. And the annihilation, they annihilate and give energy as given by this energy mass equivalence principle, E equal to mc square. So what you get is two 511 keV gamma rays, 511 keV being the rest mass energy of the positron and the electrons, going in the opposite direction. If they are at rest, you get two of the 511 keV gamma rays going exactly 180 degrees to each other. So now you know what a positron is. Positron is an antimatter. You have been introduced to it. Antimatter of electron. It has the same mass of electron. It has positive charge, and when it meets an electron, it annihilates, giving you two 511 keV gamma rays. Now, so how can you use positron as a probe? To understand that, what you need to do is you need to understand what happens when you put positron into a material, right? And what all signals can you extract when you put positron into the material? So when you put positron into a material, one of the things that can happen is you can get back positron itself through scattering. And that can be used for various diffraction experiments. I have pointed out here low energy positron diffraction or reflection high energy positron diffraction. But I'm not an expert in that field, so I'll not be talking about that subject matter here. But the diffraction experiments using positron has several advantages over electron diffraction, and it can be a talk for later time. It can also result in the emission of secondary electrons. So the positron, if it is coming with enough energy, can knock out electrons from the material just by impact ionization, just like a big guy coming in and knocking out a smaller guy. So if you have enough energy, you can knock out electrons from the material. The secondary electron emission just depends on the energy of the incoming positron beam. You just need to have a threshold energy. Above this threshold, you will start knocking out electrons from the material. And this is one of the ways in which the positron loses energy as it goes into the material. Okay, it shares its energy with other electrons of the matter. The electrons who have energy greater than the work function of the material, work function being defined as the amount of energy required to take an electron out of the material. If that the energy given to the electron is greater than the work function, then the electron will make it out of the material. So as the positron goes into the material, it will continue to lose energy. It will continue to lose energy via a variety of methods: plasmon excitation, electron hole pair excitation, phonon excitation. That phonon excitation happens when the positron energy is extremely small. When I say small, it's close to thermal energies. That is a room temperature. I think 300 Kelvin is approximately equal to 25 milli electron volt. Electron volt is a unit of energy, and 1 eV is 1.6 times 10 raised to minus 19 joules. So it's an extremely small unit of energy. So at room temperature, the energy of positron will be only around 25 millielectron. So just before it reaches the thermal energies, the last excitations that it is possible to do are phonon excitations. And once it reaches this thermal energies, then it is not able to do any more excitation. And then what it does something called a random diffusion. It just walks around like a drunkard, and just knocks here and there. And this process is called random diffusion. And towards the end of its random diffusion, it might find an electron and annihilate, resulting in two 511 keV gamma rays. So I have shown the positron to be going into the material here. That is not necessarily true. If the positron is implanted close to the surface of the material, there is also a chance that it will diffuse back to the surface of the material, and then it will get, there is a chance for it to come out of the material as positron itself. It's called positron re-emission. And sometimes what happens is the positron on its way out can pick out an electron and form another exotic species called positronium. Now, that is what is shown as the red and the blue together. So positronium is something very similar to hydrogen atom, just that instead of a proton and an electron, you have a positron and an electron. Now, again, that positronium can be used for spectroscopic technique. That is again for another day. The third thing that can happen is the positron which comes to the surface can annihilate from the surface. It will annihilate at the surface of the material, again giving you two 511 keV gamma rays. And following the annihilation, there may be emission of electrons. And this emission of electrons can also be used to study the surface of material. Now, in this talk, I would be talking about, I would be introducing three techniques. Two of the techniques utilizes this gamma rays that is coming out of the material, the 511 keV annihilation gamma rays emitted as a result of the annihilation of positron with an electron. And the third technique will be utilizing this electron, which is emitted following the annihilation of positron at the surface of a material. So the key points to take away is the at the time of positron annihilation, positron has extremely low energies, and you can almost assume that it has zero energies when compared to the energy of the electron with which it is annihilating. Just remember that point in your mind when we go forward. Now, positron loves open spaces. It does not like quarantined. Okay, it's not a person who will like this atmosphere. What I mean by that is, let me show you what a positron will feel when it is inside a material. So what you're seeing here on the x-axis is the distance from a graphene layer. Okay, so what we have done here is we have calculated the potential experienced by a positron when it is inside a specific sample. The sample here being a single layer of graphene. You can see the C is there, right? That is graphene, which is grown on a substrate of copper, and that is the copper given over there. Okay, and so a positron is a positive particle, feels the potential as shown here. Now, at least some of you, at least people in the first year masters or the final year masters course should kind of identify this potential given here, right? Wherever the ion cores are there, like wherever copper is there and wherever carbon is there, you see the tall towers going up, right? That is positive potential, which is due to the repulsion of positron by the positive ion core, right? So you have an ion core there. Say, for example, if you have carbon there, carbon has 6 protons, 6 neutrons, and 6 electrons. Now, but when it forms a graphene, a part of its electrons is donated to the valence band, and the ion core consists of the nucleus and only the core electron, which is tightly bound to the nucleus, right? So that has a net positive charge. That is what is meant by positive ion core. And so positron, since it has a positive charge, it stays away from a positive region, and that is why it has this repulsive potential which is going up. Okay, and if, as I told you, this resembles the block potential that you would have seen in the case of an electron. Now, what would be the potential like? Just think, what would be the potential like if it is an electron? The potential would be just the opposite of this, right? So a positron is exactly similar to electron, just that it has a positive charge. So for an electron, it will be an attractive potential at the positive ion core sites, right? Where if you put an electron inside that, it will feel attractive potential towards the ion cores here. So you will see that the potential given here will be exactly opposite to that. Anyway, so the positron tries to be away from the positive ion cores because of this repulsion. And I'm showing another view of it. I'm just looking at from the top of it, and each of these blue balls is where the positive ion core is, right? So the positron undergoes this diffusion mainly by knocking around because of this repulsive potential. And if it finds a region where there is less repulsive potential, okay, in this figure, what I've shown is an absence of ion core there. Now that is called a defect. In this specific case, it is a mono vacancy. Okay, wherever an atom should have been there, it is not there. Okay, that is why it is called a vacancy, and it is a defect. Normally, it should have been there, but now it is not there. Now that is an open space. Okay, so where the positive repulsion is less, and so the positron tries to be there than anywhere else. And you can see that I have shown the potential experienced by the positron again on the bottom side. At everywhere else, it has slightly higher energy than when it is at this mono vacancy region, because it is experiencing less repulsive potential, and it will be at a lesser energy. So everything tries to be at a lesser energy. The positron again tries to be at lesser energy. It tries to go into this open spaces. So this is one of the key points that you need to remember, that the positron loves open spaces, and if it finds within its diffusion any defect like open volume regions like mono vacancies, di vacancies, or large pores, And what is the biggest defect that you know of? The biggest defect is nothing but surface. Surface is the biggest defect, right? You have a very nice periodic structure, and suddenly there is a termination of that periodicity at the surface. And surface is also the most biggest open space that positron can find. So if positron is within the diffusion length from the surface, positron will go into the surface. And if it is within the diffusion length of a defect, it will go into that defect site. And that is called something called trapping. Now, once it is trapped, it will annihilate from that trap itself, and you will get a 2,511 kV gamma ray. So positron is a self-seeking probe. It seeks the defect by itself. If you compare it to some other technique like transmission electron microscopy and things like that, the observer, that is the person who is doing the experiment, has to hunt for the defect, try to go and see where the defect sites are and try to image the defect for you. But in this case, the probe hunts the information for you. That's one big advantage. The only thing is that it has to be within the diffusion length of the positron. Otherwise, the positron may never, if the defects are too small, if the defect density is too small, then positron may not see them within its diffusion length. But otherwise, it would find the defect for you. So positron loves open spaces. And why it loves open spaces? It loves open spaces because it tries to be away from the repulsive potential of the positive ion core. Now, with this information, with this much information, let's go forward and see the first spectroscopic technique that is widely used, which is called positron lifetime spectroscopy. So let me recap some of the properties of the positron that we just learned. Is that positron is the antimatter of electron. It has positive charge, same mass as that of electron. It loves open spaces. It tries to be away from the positive ion core. It hunts for defects or surfaces by itself, and it tries to be there. It gets trapped there when it is there and annihilate from those positions. And 4, after it annihilates with an electron, it will give you 2,511 kV gamma rays. Okay, with this much information, let's go ahead and see what do we do in a positron lifetime spectroscopy. So let's go back and see the decay equation here. So sodium-22, when it decays, I told you, into neon, its daughter nucleus, and a positron, it emits almost simultaneously a gamma ray, which is of energy 1.28 MeV. Now, if your eye had a sensitivity to those gamma rays, then when you see that gamma ray, you can clearly say positron is born, right? Because that emission of gamma ray is associated with the emission of a positron. So if you have a timer now, you can start the timer. And when the positron annihilates inside the material, and when it gives you a 511 kV gamma ray, and again, if you are sensitive to that 511 kV gamma ray and you see it, you can stop the timer and you say positron is dead. And what you have measured in your timer is the amount of time the positron has spent inside the material before it has annihilated. Okay, and this is what we do actually in positron lifetime spectroscopy. You do not use your eyes to do it. You have detectors which are sensitive to gamma rays. So as I shown here, you have a set of samples. You have a positron in between them, and then you have 2 gamma rays coming out. Mind it, these are not the 2 511 kV gamma ray coming out. One of them, let's say the red one is the 1.28 MeV start gamma ray. Okay, so the 1.28 MeV start gamma ray, when it reaches detector 1, tells you, hey, detector 1, positron is born. Now, when the 511 kV gamma ray reaches detector 2, it tells the detector 2 that positron is dead. And what you do is you time the time difference between them, and then you build a spectrum out of it. And this is an example spectrum of a positron lifetime. This is on the x-axis is the time, whereas in the y-axis you have counts. The y-axis is plotted in a log scale. Okay, and so I hope some of you guys know what a spectrum is, but for those who do not know, how do you construct a spectrum? Basically, you look at one positron and say you find a positron which has lived till 1 nanosecond. Okay, so then you'll go to 1 nanosecond and put one point there. Then you will look again at another positron and say now it has lived for 2 nanosecond. Okay, then you will go to 2 nanosecond and put a point there, and then you look at the third positron and now you see that it has the third positron has lived for 1 nanosecond, so you go back to your 1 nanosecond bin and put one more point there, and so on. You built the spectrum. Okay, and so this is an example spectra. For the time being, just forget what is below this 0 point. Okay, forget about it. Now you look at this spectra here. Remember that the y-axis is in log scale, and you basically have almost a straight line there. Okay, with that information in mind, what do you think the spectrum looks like? Okay, what do you think the black line here denotes? People who have taken physics in their +2 should be able to identify this. What kind of decay is that? This is an exponential decay, right? So it is nothing but an exponential decay there, as given similar to your radioactive decay. I've given the radioactive decay equation there. N is equal to n0 times e to the power of minus t by tau, where tau is the
decay lifetime.
Yeah, it's the decay lifetime. Yeah, that's right. So in this case, what you tau denotes the average lifetime of the positron. So it's not the lifetime of one positron, but it's the mean lifetime. So you have looked at several 100,000 positrons and you made the spectrum, and then you see that on an average, positrons live for tau picoseconds. Pico is 10 to the power of minus 12 seconds. So normally positron lifetimes is in that range. Okay, so tau picoseconds. And so, okay, so you measured the lifetime of positron. Then what? What does that information give you? Now, the lifetime of positron, the amount of time the positron spends inside a material, is inversely proportional to the local electron density, which is very reasonable, right? Even you can think that is reasonable. If there are more positrons, there is more chance for positron. Sorry, if there are more electrons, there is more chance for the positron to annihilate, right? And if there are less electron, there is less chance for the positron to annihilate. So it depends on the electron density. Higher the electron density, lower will be the positron lifetime. And lower the electron density, higher will be the positron lifetime. So it is talking about what we are talking about is the local electron density. So let me give you an example here. Let me go back to our earlier picture, and let me tell you what it means. So let's assume that this blue spheres represent a matrix of carbon atoms. Okay, and each of these blue spheres are carbon ion core. Okay, so carbon has, as I said earlier, it has 6 protons and 6 electrons. The 6 electrons are divided into occupy various electronic levels, and you know how they are arranged, right? It is 1s2, 2s2, and 2p2. But when it forms a structure like graphite or graphene, it is in sp2 hybridization. And so some of those electrons are in the valence band, or I would say a common bank for all the atoms here. Okay, it's in the valence band. It does not actually belong to only one atom. So the electrons which is truly belonging to one carbon atom is its s electron, one s electron. Those two electrons are tightly bound to the carbon atom. And now when you remove a carbon atom from its original position, you are not removing just the nucleus, but you are removing that carbon nucleus along with the two electrons. So locally, you are reducing the electron density there. So if your positron finds a defect, okay, and annihilate from there, it will have a very specific positron lifetime, because the positron lifetime, as I told you, is dependent on the electron density. And at the defect site, at the vacancy site, it is seeing a very specific electron density. Now, if it did not annihilate there, if it annihilated somewhere else, say for example, if it annihilated in the interstitial position, just to define, interstitial position is the position in between the ion cores. If it annihilates at the interstitial position, it sees a completely different electron density. It actually sees more electron density, more local electron density than it will see in a defect site. And that will give you another lifetime, which I've shown here as tau1 and tau2. And that is what you see here. When you deconvolute your spectra, you can see that your spectra can be deconvoluted, in this specific case, can be deconvoluted into 2 lifetimes here. I have shown the first component by a light a cyan color, and the second component by dark blue color, right? So those 2 components are telling you that in this material, in this specific material where I have measured the positron lifetime, some of the positrons are annihilating at a place where the electron density is small, and and it is also annihilating at some other location where the positron where the electron density is large. And normally, you know that the reduction in electron density has to happen because of the removal of a defect site, and because positron likes defect sites, it is more likely to go there and annihilate. And for each defect structure, for in each material, there's a specific number for them. Okay, so for example, I have given here the lifetime of a positron as a function of the size of the vacancy. Okay, so 0 means it is a defect-free material. Okay, so if the positron is inside a defect-free material, and the material here is a well annealed, well heated ion sample. Okay? So if there are no defects inside the material, you will get somewhere close to 110 picosecond. 110 times 10 raised to minus 12 seconds. Okay, that is 110 picoseconds. Now, as soon as you introduce defects, which is having a characteristics of mono vacancy, that is, it is missing only one ion atom, then your lifetime increases to close to 190 picoseconds, right? And as you go further on, as you keep increasing the size of your vacancy, you can see that your lifetime increases. Now, beyond a certain point, you cannot see a variation in the lifetime. That is because positron is given the energy of the positron, the de Broglie wavelength is extremely small, and it will not be actually seeing the electron density so far away. Okay, that's why you do not see any more variation. But you don't have to worry about it if you don't understand that. Mainly, you can see, say, up to 10 to 15 vacancies. That means 10 to 15 vacancies together. It is not 10 to 15 vacancies apart. It's one big vacancies which is made by removing 10 ion atoms. Okay, so you can see up to that. You can clearly look at the numbers and can predict what is the type of defect present in your material. Okay, so that is one information that positron lifetime spectroscopy gives you. What is the type of defect present in your material? Now remember, the strength of positron lies in small, right? In mono vacancies and di vacancies, it will give you very large difference in positron lifetime. Not in vacancies which is extremely large. You have transmission electron microscopy and high resolution transmission electron microscopy to see defects which are greater than 10 vacancy cluster. You can use TEM for that. But for seeing a single atom vacancy, it is very difficult to do that using transmission electron microscopy, and positron is the best tool available to do that. So one, it will give you the information what kind of defect is present in your material. Two, the intensity of each of this component. Okay, how much tau1 is present, how much tau2 is present, will tell you what is the defect intensity in your material. Say, for example, what concentration of mono vacancies are present in your material, what concentration of di vacancies are present in your material, and so on. So positron lifetime spectroscopy can give you the defect density and defect type. And this is extremely important for a whole lot of material science projects. And some of you guys who are in research can think of it, because defects play an important role in electronic optical properties of the material, and hence it is very important to know what is the defect structure of your material. Okay? So you can use positron lifetime spectroscopy if the need arises. So now let's go over to the second spectroscopic technique I will be talking about, which is called Doppler broadening spectroscopy. Now, when the positron annihilates with an electron, remember that in the earlier picture I had shown a free electron annihilating with a free positron. But in this case, when it is inside a material, the positron is actually annihilating with a bound electron, right? And so the annihilation has to conserve what? Energy and momentum, right? It has to conserve energy and momentum. Again, this is +2 physics. The energy before annihilation, which is given on the right hand side, should be equal to energy after annihilation. So after annihilation, you get two gamma rays. So the energy of the first gamma ray is gamma 1, and energy of the second gamma ray is gamma 2. And what is the energy before annihilation? The energy before annihilation is the rest mass energies of positron and electron. The rest mass energy of positron is m0 c square, and rest mass energy of electron is m0 c square. So their combined rest mass is 2 m0 c square. And there is this additional term here, EB. What is that? It is the binding energy of the electron, right? So the electron is bound and it has a finite energy when it is inside that material. And that's what it is included here. Now the question is, why don't I include the energy of positron here? Remember, I told you before the annihilation, in most of the time, positron is at thermal energies, and then it is only like milli electron volt energy. So you can ignore that in this equation. Okay, so that's why I've approximated the energy of positron to be 0 here. So this is my conservation of energy equation. And the second part is conservation of momentum. So the right hand side of this equation here is the momentum of the electron positron system. Okay, it's the momentum of the combined electron positron system, and there is this mark here, which is two lines denote parallel. I am writing this conservation of momentum in one direction. Actually, you can write conservation of momentum in all three directions, right? Px, Py, and Pz. I am writing this conservation of momentum in one particular direction, P parallel. That means the momentum of the electron positron system, which is parallel to the direction of gamma rays. So after annihilation, the gamma ray travel in one particular direction. The momentum which was parallel to that gamma ray direction, that is P parallel there. Now that should be that. So that is the momentum before annihilation, the momentum of the electron positron system. And what should be it after annihilation? It should be E gamma 1, E gamma 2 divided by C minus E gamma 1 divided by C. So people who cannot identify this, so normally what you do is it's a photon. You cannot use P is equal to mv to denote the momentum. So what you do use is the equation E is equal to Pc, right? From E square is equal to P square C square plus m0 square C raised to 4. In that equation, the rest mass energy of the photon is 0. So you end up with E is equal to the momentum P times C. So the momentum can be obtained by dividing the energy of the gamma ray by the velocity of light. So E gamma 2 by C is the momentum of the second photon, and E gamma 1 by C is the momentum of the first photon, right? So using these two equations, this conservation of energy equation and conservation of momentum equation, you can calculate what should be the values of E gamma 1 and E gamma 2. right? This is two unknowns, two equations. You should be able to do this again. Should be like a 10th or even smaller grade mathematics, right? So one of the things you can do is just add these two equations, right? So before that, you just multiply the conservation of momentum equation all throughout by C. So you would see that E gamma 2 minus E gamma 1 is P parallel times C. And then if you add these two equations, you can get E gamma 2. And then if you subtract these two equations, you will get E gamma 1. And I have calculated that E gamma 1 and E gamma 2 for you there. And then you see that there is N0 C square there. Okay. There is minus EB by 2 there. That's also okay. And then for E gamma 2, you get an term added to it. And for E gamma 1, you get a term subtracted from. Now, what is this? This is nothing but your Doppler effect, right? You would have learned that again, +2 physics. So if I have a detector here, and if my momenta of the electron-positron system is towards my detector, it will result if the momenta is towards my detector, then it will result in a blue shift, and if it is away from it, it results in a red shift, and that is what is given by this delta E over here, right? So this is one peculiar case where I know which direction the electron positron system is moving. Okay, but in reality, I really do not know. When I do the measurement, I do not know which direction the electron positron system is moving, and hence what happens is I measure both positive shift and negative shift equally with equal probability. And what happens is my gamma ray, which should have been ideally a Dirac delta function, means that means just a straight line over here. It should have been 511 kV all the time, right? But instead of that, what you get is this broadened line shape. You get this broadened line shape. It will be broadened on the higher energy side, and it will be broadened on the lower energy side, and this is called Doppler broadening. Now again, let me go back to the one point I asked you to remember. Before positron annihilates, positron has almost zero energy. So the momenta of the electron-positron system is dominated by the momentum of the electron with which the positron is annihilating. So this broadening is direct indication of the momenta of the electron in a direction parallel to the emission of gamma rays. Okay, so you are basically, by measuring that broadening, you are basically measuring the momenta of the electron with which the positron annihilated. Please note, you are measuring the momenta in one direction, one particular direction, and I have called the direction as P parallel. Now this delta E, as I've shown here, is P parallel C by 2. And again, you can see that, right? So the way I've defined delta E, here is you have a delta E on E gamma 2, and then you have a delta E on E gamma 1. And so if you take E gamma 2 minus E gamma 1, you will get 2 delta E, which we said E gamma 2 minus E gamma 1 is P parallel C. So 2 delta E is nothing but P parallel C, and so delta E should be P parallel C by 2. Now, so this momenta is mostly reflective of what? The momentum of the electron with which the positron annihilated. Now, do you know the relationship between momentum and energy? P square by 2m, right? P square divided by 2m gives you the energy. So the broadening that you measure, delta E that you measure, is directly proportional to the square root of the binding energy of the total energy of the electron. And so if the binding energy goes up, the broadening goes up. If the binding energy goes down, the broadening goes down. Now, when does the binding energy goes up? The binding energy goes up for electrons as the electrons move closer to the nucleus, and the binding energy is lower when it is away from the nucleus. Naturally, when you say when it is away from the nucleus, you said it is loosely bound, right? That's what we learn in our +2 physics class. It is like loosely bound. So the binding energy is lower. So I have given an example here. if a positron annihilates with a 1s electron of graphite, that means carbon, you get a delta E of 7 keV. Okay, that's such a large broadening. So you get broadening all the way up to 511 to 518 keV. Now, if a positron annihilates with a valence electron, means a loosely bound electron, say the 2p electron of carbon, then you get roughly around 1 keV broad. Okay, so again, we do not know which electron the positron is annihilating with. So the line shape here represents a combined effect. Positron annihilates with 1s electrons, positron annihilates with 2s electrons, it annihilates with 2p electrons, and so on. And then what you measure is a convolution of all this contribution. Okay, so how is this information important? What kind of information can you get from Doppler broadening spectroscopy? Let's go back to our picture again. Okay, so if you remove, as I told you, if you remove an ion core, you're removing an ion core along with its 1s electron. So what have you done here? You have removed a set of electrons who are having higher binding energy, right? You have removed the 1s binding energy of carbon is around 280 electron volts. So you have removed those electrons. So now a positron who is annihilating from it has less possibility to see and annihilate with 1s electron, and hence the resulting gamma line shape will be narrower. It has to have lesser broadening, right? But if it annihilates with say in the interstitial region, then it will equally likely see the core level as well as the valence level. So if it is annihilating at a non-defected region, it will be broader. Another thing that you need to remember is that the binding energy is material dependent, right? What is the binding energy? The first level of hydrogen atom, it is negative 13.6 eV, right? And for that is the oneness of hydrogen, and for oneness of carbon, it is 280 eV. So this binding energy is actually a material dependent, highly dependent on material, and so it's not only defect structure that you are now sensitive to, you are also sensitive to the chemical species. And this is given here in this nice Doppler broadening spectra, which was taken on silicon, gold, and as an example, defected gold. Now you see that there is a huge difference in line shape between silicon and gold. Gold is given as red and silicon is given as black. Okay, let me just quickly point out what this x-axis point to. The 0 here corresponds to 511 keV gamma ray. And I am expressing the x-axis in terms of the shift, the Doppler shift. So 1 means 1 keV Doppler shift, 2 means 2 keV Doppler shift, and so on. So 2 here corresponds to a gamma of energy 513 keV, 511 plus 2 keV. And negative 2 here corresponds to 511 minus 2, which will be 509 keV. Okay. So this is the same as a gamma ray energy. So you can see that the line shape is dependent on the chemical nature. You can see a difference between silicon and gold, and it is also dependent on the defect architecture. So Doppler broadening spectroscopy can give you two information. It can give you the nature of, it can give you the defect density in your material, and it can give you the chemical nature at the site the positron annihilates, and that is very important. So in some cases, the properties of the material are defined by the defects, but it is also defined by what are the chemical species surrounding that defect. What is around that defect region, whether it is an ion, whether it is copper or something like that. So that defines the property of that material. And so Doppler broadening spectroscopy actually can tell you what is decorating your defect. And again, so if you are looking for that kind of information, is that you want to know whether your material is defected, and if you want to know what is the chemical nature at the site the positron annihilates, Doppler broadening spectroscopy is here too. Now, compared to positron lifetime spectroscopy, one drawback for Doppler broadening spectroscopy is that you cannot get a quantitative information about the defect. That means you cannot identify what is the defect type. Remember, for positron lifetime, for each defect type, you had a specific lifetime. That information is not available here. And defect density is also not directly available. What you get is a coupled information. You will get broadening, like you can see that you will get a variation in line shape, whether due to an increase in defect density. When I say increase in defect density, it means that you are increasing the number of defects. Or you will get a change in line shape when you change the defect type. Say, for example, you are going from mono vacancy to di vacancy, or di vacancy to a 4 vacancy cluster, and so on. So both of these will give you a change in line shape, and it is difficult to decouple these two changes. So, but the overall thing is that you will see a change in your line shape, which is a combination of either the defect density changing or the defect type changing, or both of them changing. And you will get the information about the chemical architecture at the site of positron annihilation. So I hope it is clear till these two points. And let me point out to you that positron lifetime spectroscopy and Doppler broadening spectroscopy are the two major or most widely used technique in the positron community. Okay, so there are several places in India which does it. There is Indira Gandhi Center for Atomic Research, where I did my PhD. Baba Atomic Research Center, which is a sister institute. Then, as far as I know, there is positron lifetime spectroscopy was available in University of Mysore, and it is also available in Saha Institute of Nuclear Physics. Actually, the person who is responsible for positron lifetime spectroscopy in Saha Institute of Nuclear Physics is Dr. PMG Nambishan. He is a world-renowned expert in the utilization of positron spectroscopy for studying nanomaterials. Okay, so she is a much more expert than I am in positron lifetime spectroscopy and Doppler broadening spectroscopy. So he's a senior scientist there, and if you have queries or you want to send your samples, that he'll be a nice person to contact. Now, so I told you I'll be using two techniques which will be utilizing the gamma information. That was the positron lifetime, which looked at the time between two gammas. And second was the Doppler broadening spectroscopy, which looked at the overall line shape of the gamma that you measure. Now I'll jump a little, jump gears a little bit and go to something else called slow positrons. So both the spectroscopy technique that I described earlier utilizes this sodium-22 source. The sodium-22 source, which decays into neon, giving you a positron. Now the positron that comes out of this beta decay has this particular beta decay spectrum. The black one given there, that's the beta, positive beta emission spectrum. That means the energy of the positrons which is coming out is given like that. Okay, so it's not one energy, it's coming out with a whole range of energies. The peak energy is somewhere around 200 keV, 200 kilo electron volt. That means 200 times 10 raised to 3 electron volts. And this endpoint energy is somewhere around 540 keV. So you have positrons coming all the way from 0 to 540 keV, with the peak being at 200 keV. So these high energy positrons can penetrate into the material up to a few hundred micrometers. To remind you, micro is 10 raised to minus 6 meters. Okay, so it can penetrate that much deep. So the information that you are getting, the information I told you about defect density, defect type, chemical nature, all of those are coming from this few hundred micrometers. So it is an averaged information. You do not have a depth resolved information. In order to get a depth resolved information, what you should do? You should control the energy of positrons. So if you are able to get the positron with, say, one single energy, then you can accelerate or decelerate that positron to any energy that you want, and hence you can deposit the positron at the depth that you want and get a depth resolved information. And that is possible, fortunately. And the process is called moderation. Sorry, I will not explain what the moderation process is, but the most widely used moderator is tungsten. There are other kinds of moderator like rare gas moderator. Rare gas is neon. So you can use solid neon also as a moderator, but tungsten is the most widely used in our community. So what basically happens is you send these range of positron energies going from 0 to 540 keV, few hundreds of keV, onto the tungsten. And when it comes out of the other side of the tungsten, it is re-emitted as positrons with single energy. Okay. Now this moderation process is highly inefficient. That means the moderation efficiency of tungsten is of the order of 10 raised to minus 4 in the best case scenario. 10 raised to minus 4 means if you send 10,000 positrons into the tungsten, you will get one positron with the desired energy. Okay, so it is that inefficient, and hence the positron spectroscopies are a little slow, just like the slow positrons, to get the data out. It depends on your source strength. But now there are beams all over the world. There is very high intensity beam in Germany. There is high intensity beam in Japan. Baba Atomic Research Center is planning a high intensity beam in Bombay. So there are high intensity beams and there are high intensity beams in US here. So there are high intensity beams which can overcome this problem of inefficiency. But the main thing is that you can control the energy of positron, and at the end of moderation process, you get a highly monochromatic positron beam, and that is what is given by the straight line over there. So if you use tungsten, okay, the energy of the positron is approximately 3 electron volt. So, and plus or minus 0.6 eV. Okay, so it can be 3.6 eV to 2.4 eV, but it is not kilo electron volts wide. Okay, so it is an extremely narrow beam energy, and so now you have this slow positron. Now, why is it called slow positron? Because you have gone from kilo electron volt down to eV. Okay, this is extremely slow positrons. And now this slow positrons can be used to do whatever you want. Okay, you can build a beam out of it and accelerate or decelerate in the ways that you want. Now, for people who do not understand this unit electron volt, just for those, others can ignore this. Now, suppose you have a positron with energy 3 electron volt, okay, and you are sending it this positron to a plate. It's a metallic plate, which is given a potential of, say, 3 volt. Okay, 3 volt, exactly 3 volt. Then the positron, and let me tell you, it is positive 3 volt. Okay, so if you give positive 3 volt on a metallic plate and you send this 3 eV electron to this plate, just before the hitting the plate, it will get reflected back. Okay, so that gives you a sense of energy. Okay, so 3 electron volt is roughly the energy which is given by the 3 volt potential difference. Okay. Anyway, so once you have this low positron, you can build beams out of it, and you can control its motion from the source to your sample and take it to any energies that you want and do your experiment. And the picture shown here is the beam that one of the beam that I have here in my lab here. It's our lab here. It's the slow positron beam. we have built one more positron beam. If I have chance, I will show it. Yeah, and so we have two positron beams in our lab. This is one of them. So basically, what you see here on the right end is the source region, and so the black bricks kind of thing, those are lead, okay, just to prevent you from the gamma rays that come from the source. So that's the shielding there, and the positrons travel through this beam line, and in here we use magnetic field to control the positrons to from the source to the sample. So okay, so you can use slow positrons to characterize surfaces. When I say surface, since you can control their energy, you can put positrons on the surface or deep into the material. So what's the big deal? Okay, so you can characterize the surface. So what? In order to understand that, you need to understand what are the top popular surface spectroscopic techniques around, right? So the two popular surface spectroscopic techniques using electron and photon. One of them is XPS, and I believe many of you in the research would have used it. It's X-ray photoelectron spectroscopy, and then you can also have uh, 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 similar surface spectroscopy using electrons. Okay, so in both of this case, what do? You come in with a high enough energy. Say, for example, in the case of X-ray photoelectron spectroscopy, you come in with a high enough energy to knock out the electrons from its shell. So the spectra given here, mind you, this is not my spectra. I've taken it from SIA and Dench. So the spectra given here, you can see various peaks there, right? So copper 2p3, copper 2p1, copper 2s, copper 3s, copper 3p. I'm not sure whether you can see the x-axis, but the energies are like copper 2s is close to 1200 eV, and copper 3p is close to like a few hundred eV, say like 70 eV or so. Okay, so the X-ray will have an energy greater than the minimum energy required to knock out that electron. Now, if you have to knock out a 1s electron of carbon, I told you the binding energy of 1s electron of carbon is 280 eV. So if you are trying to knock out the 1s electron of carbon using a photon, you have to use a photon having an energy higher than that binding energy. Only then you will be able to get the electron from inside the material out into the vacuum beyond the dipole barrier. And so unless you give this much energy, the electron is not going to come out. So you need to come in with higher energy photons, and that is the case for electrons too. You need to come in with high energies to knock these electrons out. Now, since you are coming in with higher energies, your penetration depth is not exactly surface. In some scenarios, you can call it surface. Say, for example, in the case of this shown here, the penetration depth is shown to be around 10 nanometers, which is like 20 layers, atomic layers. So you can call it in some sense surface because it is very close to surface, but the information you are getting is averaged over this 20 atomic layer. Okay, and similar is the case of electron beam. You can see the primary excitation region, that's the blue region, where the electron goes in and causes all sorts of excitation, and you can get characteristics X-ray from that region. You can use it for characterization, and you can get backscattered electrons from that region. And please note, and to 2 points here, secondary electrons, you see the secondary electrons are coming very close from the surface of the material. Similarly, OJ electrons, it is given here that it is coming from 0.5 to 5 nanometer. Actually, it is much more surface sensitive. OJ electron emission is much more surface sensitive than the XPS. So the surface sensitivity of both XPS and electron-based electron spectroscopy is not based on the probe. It's not the probe which gives you the surface sensitivity, because the probe goes deep. what determines the surface sensitivity is something called the inelastic mean free path of the electron which is trying to come out. Okay, say for example, in this case of XPS, an X-ray photon comes in by photoelectric effect, right? You know, E is equal to h nu by photoelectric effect. It knocks out an electron from the, in this case it is copper. It knocks out an electron from the copper, and that copper electron, now the photoelectron, is trying to come out of the material. Now when it is trying to come out of the material, it will lose its energy. There are chances for it to collide with other electrons. It is in a sea of electrons. There is a good chance for it to collide with another electrons and lose its energy. Okay, so if it lose enough energy, then it is not going to come out. Now this graph here, in the x-axis u is given as the kinetic energy of the outgoing electron, and in the y-axis what is given as the inelastic mean free path. Inelastic mean free path is can be roughly defined as the mean distance the electron travels before a collision. Okay, so if the inelastic mean free path is small, then within a short distance there is a very good chance that it will undergo a collision and lose its energy. So smaller the mean inelastic mean free path, smaller is the chance for the positrons to come out. I can give you an analogy, like in these days, if you are trying to go out from your home, you will be stopped by police at every junction, right? If you are in a big city, there is a very good chance that you are stopped in every junction, and so the chances of you getting to your destination is smaller depending upon the number of policemen between your home and your destination. And if they find that you do not have a good enough reason, they will send you back home, right? So you will never reach your destination. In this case, destination being getting out of the material. But suppose you are in a region, say a slightly rural region where the number of checkpoints is smaller or collision points are smaller, then there is a greater chance for you to reach your destination, right? It's exactly the same thing. So if your collision chance increases, the chance for the electrons to come out is smaller. If your collision chance is lower, the chance for electrons to come out is larger. So for these spectroscopic techniques, the surface sensitivity comes from that fact. If you are getting an electron out, you are saying that, oh, since I got an electron out, it cannot be much deeper from the surface, because otherwise it would have lost energy and it would never have made out of the material. So it has to be from the few top atomic layers, say 5 to 10 atomic layers. And this is where the surface sensitivity of this electron and photon based surface spectroscopy techniques comes from. But they have one more problem. That problem is the problem of background. Okay, let me show you two spectra here. And this is the on the left, I'm showing you the electron spectra due to 180 eV photon hitting silver, and on the right you have a 3 keV electron hitting a copper. Okay, and we are looking at the spectrum is the spectrum of electrons which is coming out of that material. Now you see that the 180 eV photon actually produced a peak here at around 171 eV. That is the photo peak. It is knocking out valence band electron from the silver, and that's the through photoelectric process, and that's the photo peak there. And then you also see that there is a peak around 118 eV, which is it has knocked out a 4p electron from silver. Then you can hardly see a 4s electron there. It has knocked out a 4s electron there, and then you see this huge hump over there. That is nothing but the secondary electron background. Remember I told you that secondary electrons, when I introduce positron going into the material, it is the same thing. If an energetic particle can come in, if it can knock out electrons, it will knock out electrons. Then you get this sea of secondary electrons here. And you see, I have marked, there is something over there. There is a hump there. You hardly see it. There is an OJ line there. You can hardly see it. Similar is the case for 3 keV electrons hitting a copper. And then you see this huge background of secondary electrons. It's like going up there, and you can hardly see an OJ peak there. And I will define what OJ peak is later on. Okay, so bear with me. But the key factor is that you get this big background of secondary electrons, that you are not able to see anything in the energy range from 0 to 60 eV. You are gone. You cannot see any processes which is happening in that region. So two processes, two things. It's actually not that surface sensitive, and you are not able to see processes which involves the emission of low energy electrons. Say, for example, in the range of 0 to 20 eV, you are not able to see that. You just get this huge secondary electron background, which is due to impact ionization. So I am talking about low energy electron, which is emitted as a result of some other process, not impact ionization, not a bigger guy coming in and knocking out a smaller guy, not that. Some other processes can also result in this low energy electron emission, and there is no way that you can see it. Now, positron is surface
Excuse me.
select. So I'm getting an echo here. Can you please?
Yeah. Okay, I think it is very extended. So, excuse me.
Oh, okay. So if you want, I can stop here, or
No, you just go ahead. I understand that you are discussing something important. So please go ahead.
Okay,
But please keep an eye.
Okay, thank you very much. So positron is surface selective. Why is that? So let me show you again. Let me come back to the potential experienced by the positron on a sample which consists of single layer graphene on copper. Okay, single layer graphene on copper. So I told you that the positrons get repelled by these peaks there, right? Because of the repulsive potential. Now, if I try to find out where the positrons will be in such a repulsive potential, in such a potential, I see this. Okay, this top panel here shows you the probability density for finding a positron. Or if you put a positron on a single layer graphene copper system, where is the best chance that positron will be? And you see that the positron is the probability density peaks near the surface. So this x-axis over here is 0 is where graphene is, and positive side is on the vacuum side, that is on the outside the material, and negative is inside the material. So you see that the positron is actually just outside the material, and that is where positron is more likely to be. And why is that so? Let me show you a different picture of this. Just that it's not two-dimensional. It's just I have taken a cut and expressed it as a single dimension thing. And this is the same picture again. And you can see the repulsive potential going up due to carbon and copper up here. And I have also shown you the density there. Where is the density most higher? The density is higher at the surface, very surface, at 2 angstroms beyond the surface, and the positron probability density is decreasing rapidly as it going into the material. So the chance that the positron annihilate with the electrons of the material itself is very small. You see, this region, that's the chance. When there is an overlap with the positron probability density and the electron probability density, then there is a chance for annihilation. And so that chance itself is very small. Right? So and by the second layer, the positron probability density is gone. It has a chance to interact only with the top layer. Now, why is it so? You know what these high the thing which is going up there. I have shown here. These are the repulsive potential, which is slightly going into the vacuum. And what is the other one? What is this orange thing? That is the image potential. Any charged particle in front of a conductive material will feel an attractive potential, and which goes like 1/4Z. This is specifically should be known to people, first MSc or second MSc people who have taken classical electrodynamics. You would have done method of images to solve the problem, right? So you would have come up with this problem there, where you will solve the problem for the potential experienced by a charged particle in front of a metal surface, right? So that's the image potential. Now, These two potentials combined will give you a potential well over there, and the positron actually gets trapped in this potential well. It has lower energy than being in the interstitial regions, and so hence it prefers to be in the surface. And that is where the surface sensitivity of positron technique come from. The probe itself is surface selective. Okay, probe wants to be in the surface. Probe selects the surface. Now, as I told you, when you put a positron in, it goes about its normal processes and then comes back and falls into the surface region, and it traps there and it annihilates from the surface. Now, what about the second thing? Okay, before going into the second drawback in the electron and photon case, which is the secondary background, let me tell you what positron annihilation induced OJ electron emission is. Now, this definition is actually true for any OJ emission. Only in photon and electron case, the method of producing the primary core hole is different. Okay, let me explain for the positron case, and then we'll go into, I'll just brush upon electron and photon. So when a positron comes, it annihilates with a core electron and it produces a hole there. Now that hole, that absence of electron, is filled up by an electron from a higher level. And so this energy, so this is lower energy, which is at the higher, at the valence band, lower energy, you are having higher energy there. So you are having an energy difference, right? You are gaining energy by dropping into the this core level here. Where does that energy go? Now that energy is given to a third electron, which comes out. Now such a process is called OJ process. In principle, it should be called OJ Meitner process, because both OJ, Pierre OJ and Lise Meitner saw those almost simultaneously. I think Lise Meitner saw it first. Okay, so you have this OJ emission process. Now this OJ emission is again dependent on the energy of the OJ electron which is going out is dependent on the energy of the electron levels, right? First, where the hole is created, next where the electron is falling down, that is EZ, and then next where the electron is going out from, EY. So the energy of the OJ electron is given by this equation here. Simple equation. It is just energy conservation equation. The energy of the primary hole minus the energy of the hole which is falling down. So that's the energy difference that you have. That energy is given to take out a third electron, which is EY. And then you need to have at least the work function to get the electron out of the material. That is phi minus. So this is just an energy conservation equation, and that's the energy of the OJ electron. And from the energy of the OJ electron, you can identify what kind of chemical element is here. Now, remember, how did positron create this core hole? It created this core hole by annihilation. Now, in the case of electron and photons, if you wanted to create this core hole, you have to come in with an energy of Ex and more. Okay, only then you would able to knock out. You are knocking them out. But in the case of positron, you are annihilating. There is no knockout process happening. You can come with zero EV energy and still have this OJ process possible. So what is the advantage? The advantage is that you can come in at extremely low energies. Energy is lower than the minimum energy required to get the electrons out. Okay, so you can completely avoid the electron background, which was prohibiting electron and photon based spectroscopic technique to look at 0 to 20 eV region. Okay, now just to tell you the naming convention, if you have an OJ electron produced in a core level C, and if you have two electrons coming from the valence level, then it will be called CBB. Say, for example, in the case of carbon, 1s electron, it's a K shell electron, right? If you produce a hole in K shell and an OJ process happens by a valence electron falling into the K shell and then a valence electron going out, then you will call that OJ peak as KBV. So you can identify which all electrons took part in it. Okay, and there you go. I'll show you the removal of secondary electron background. On the left side is the same spectra that I showed earlier. You see, you hardly see a bump of copper MVV OJP, but when you use positron annihilation induced OJ electron spectroscopy, because you can come in with energy less than this. In this specific case, I have come in with energy at 25 eV, and hence your secondary background is much removed from the from the actual OJ peak, and you can clearly see the OJ peak. Not only the M23VB, there is also an M1VB, but we will not go into the details of that now. So now in this specific case, I have come in with 25, but you can come in as well with 1 EV. So let me quickly introduce you to the experimental apparatus. We are running a bit short of time. So again, this is my experimental apparatus. So how do you measure this OJ electron energy? What we have is the positron source. Positron goes into the sample. It is guided to the sample using a magnetic field in our case. It reaches the sample. It annihilates with an electron. And sometimes it results in the emission of an OJ electron. Now this OJ electron travels back to a detector which is kept at the center of this whole thing. It travels exactly 1 meter before reaching this detector there, and you detect the electron. And why do you do this? So we actually do not measure the energy of the electrons directly. What we measure is the time of flight, or the amount of time the electron took to travel from the sample to the detector. Can you measure that? Yes. So when the positron annihilates with the electron in the sample, you get a 511 keV gamma ray. Okay, and only after that annihilation, an OJ process happens and an OJ electron is emitted. Right. So the detection of 511 keV gamma ray tells you that okay, a positron has annihilated. Expect an OJ electron. Now, when an OJ electron starts and when it reaches the MCP, you detect an electron and you say, hey, I have detected an electron. And the time difference between these two gives you the time of flight. Now, how is the time of flight related to the energy? Again, plus 2 physics, half mv square. And v is nothing but L, the distance traveled by the time taken. You are measuring the time there. So the kinetic energy is proportional to 1 by the square of the time of flight. So if you measure time of flight by using this conversion equation, you can directly go into the kinetic energy of the electrons. So how does the time of flight spectra look like? Okay, so this is a representative time of flight spectrum. This is from copper. The black is from copper and the red is from single layer graphene. Let me give a brief outline of the sample here. So the single layer graphene is actually grown on a copper substrate. It's just one layer of graphene on a copper. We took the spectrum, the phase spectrum, and then what we did is we cleaned the spectrum, cleaned the graphene out. That is, we sputtered it out. We kind of rubbed the graphene away, and we get a clean copper there. And then we took the spectra again, and you clearly see differences here, right? So let me point out to the peaks over at the left region here. Before cleaning, the main peaks that you see is carbon KVV. I hope you know what KVV means. And you have oxygen KVV peak. Okay. And after removal, what you see is you don't have any carbon and oxygen anymore, and you have copper there. Copper MVV peak. So now you know that you're looking at copper. Now, what is this huge peak in this region here? Obviously, they are secondary electrons because I'm coming in with 6 EV, 6 electron volts. Now, the 6 electron volts is bigger than the work function. Work function is around 4.5 EV. So you should get secondary electrons. So you would be scratching your head and saying, hey, I just said positrons can be used to remove the secondary electrons. Yes, it can be used to remove secondary electrons. Now, what I do is, instead of using 6 EV positrons, I use 1.25 EV positrons. 1.25 is much lower than the work function for single layer graphene or even copper. Both of them are around the work function. The energy required to remove the electron is around 4.5 to 5 EV, much smaller than that. So there is no secondary electron happening. So boom, your low energy secondary electron background is gone. And what you see is only the copper peak and what is called a low energy electron tail due to the copper. That means this OJ electrons, when it comes out of the material, remember the inelastic mean free path? When it comes out of the top layer, it loses some of its energy to nearby electrons, to the electron C, and some of those electrons also come out. So those come out with smaller energies, and that's what you have. Now, what should the graphene should look like? So graphene should have a nice carbon and oxygen peak and a tail like this, right? A small tail which is going there. But no, lo behold, there is lot of intensity up there in the low energies. Okay, what is that? And so we were confused because we were at energies 1.25 eV. There is no way that we will get electrons other than due to annihilation process, annihilation induced OJ process. Now, what OJ process can give you this low energy electrons? So we went back and looked at the valence band density of states of graphene. Now, density of state for the people who really do not know, it will give you on. So I've tilted this density of states upside down here. I've given like a 90-degree rotation. So the density of states is in the top axis, and the energy is in the on the vertical scale. The density of states basically gives you the number of electronic states available for the electron at a particular binding energy per unit volume. That's where the density comes from. So it can be per unit volume of a unit set. Okay, so it can be density of states per unit set. So this is the calculated density of states of the graphene. And this blue region for graphene is the filled electronic level. So you have electrons filling all the way up to this level called Fermi level. You don't have to worry about the technicalities of what the Fermi level is and things like that. And this green region is the conduction region where there are no electrons right now. Now let's see what happens. Now if a positron annihilates with this electron, which is deep inside this valence band of the graphene. The valence band of graphene is actually quite deep, which is quite unusual. It is 18 eV deep. Now this hole can be filled up by an electron from somewhere in the band itself, and that energy can be given to a second electron, and that electron can come out. Now remember, this is different from the OJ process that I showed you earlier. Earlier, the primary hole was created in the core level. Here, the primary hole is created in the valence level itself. So what will you call such an OJ process? V. And this is the first, we were the first people to actually observe this VVV process. So again, why we were the first people to look at it? Because of the energy of the electron which is coming out. It is between 0 to 20 eV in the same region where the electrons and photons cannot see because of the secondary electron background. Now, when I say I understand the process only when I can model it. Okay, that's what physics is. So this is the last equation I show you, and probably the second last slide. And I hope to at least have some people understand this equation. Okay? So how will you calculate the energy spectra of an OJ process which is happening due to VVV? Okay, so the positron comes in, annihilates with an electron, it produces a hole, and you need to find out how many such holes are possible in this valence band density, right? So at this energy level, you know these many number of electronic levels are there. That's the density over there. These many number of electronic levels are there. And so that many number of holes are possible, right? So first you need to know how many number of holes can be created. There you go. So that's the density of holes that is created by the positron. Then an electron should fall into there. So there are variety of ways in choosing this electron, right? You can choose this electron from anywhere inside this valence band, and at each energy you have a specific number of electronic levels possible. So the number of electrons that can fall from there is directly proportional to the density of states there. So you multiply by that, so it falls in. Now this energy should be given to a second electron, right? How do you choose the second electron? Again, the second electron can be chosen anywhere within this valence band. And so you need to multiply that with the number of ways you can choose this second electron. Again, you multiply with the density of the second electron. So density of holes, density of the first electron, density of the second electron. Now, can this EH, E1 and E2 be independent? No, they are not independent. They are related by this energy conservation equation. So there you go. I have written an energy conservation delta function. So MSc first year and MSc second year students should understand what this means. So if this delta function is satisfied, this term remains, otherwise this goes to 0, right? So you cannot randomly select EH, E1 and E2. EH, E1 and E2 should satisfy this process such that EH minus E1 minus E2 minus E5 minus, sorry, E5 minus EA should be equal to 0, right? And then you should integrate this over all energies possible. And that's how you find out the spectra of electrons coming out due to this energy process. And fortunately for us, what we thought was BVV process was BVV process. So the black is the experimentally measured spectra, and the red is the spectra which is just calculated using the convolution of the density of states that I have shown here, or the integration over the density of states I have shown here. And since we also calculated the spectra, we also calculated what is the probability for a hole in the valence band to decay via this process. And we found that the OJ decay probability is 1. That means almost 100% of the time, if you create a hole deep enough in graphene, it is going to decay via an OJ electron emission. And where is this important? So you start off with one hole in the valence band of graphene, you end up with hole multiplication, you end up with 2 holes in valence band of graphene. And there is also studies which says that this low energy electrons is actually very pertinent in causing DNA strand break. And there is also studies which shows that these low energy electrons interacting with the celestial molecules is the cause of the origin of life. Okay, so there you go. Questions? I'm sorry I took a little bit more time than permitted. But yes.
Thank you, Dr. Varghese. It was a really excellent talk, and I understand the difficulty with the participants because we have got a wide spectrum of participants from 10th standard up to this university professors. So naturally, and you have tried your best to accommodate all the participants in your talk, and I appreciate that. And so we'll take a few quick questions. Here we have a few questions in the chat box. I'll just read out. I suppose you'll be able to figure out. So first question is from Bhattachaji Govind from Delhi. He has asked, what was the result of LHC experiment on antimatter? Did it lead to any better insight on our understanding on the tiny excess of matter over antimatter?
So this is not my area of expertise. I'm not a high energy physicist. Sorry to disappoint you. I do not know the answer. So as far as I understand, presently there has been no understanding of the problem causing that we have an excess matter than antimatter. So what people are looking for is something called a neutrino problem. What they're trying to see if neutrino is its own antimatter. Such particles are called Majorana. Okay? So they are trying to see if neutrino is its own antimatter. If that is the case, now that can explain the excess matter that we see in the universe. There are people in my university that do this neutrino experiments. As far as I know, they have not been able to show anything anything concrete till now. They are still in the process of doing it. But it's better that you talk to experts about it.
Yeah, she has asked a question. How can we understand God particle or Higgs boson particle with context to matter-antimatter interaction? The same question.
Yeah, sorry. Again, let me clarify. Very much clarify to you is that I am a material scientist, a content matter physicist. So I will not be the best person to answer this question.
Correct. There's another question. There is, sir, in materials undergoing photoelectric effect, will the lifetime of positron be higher? Can we understand the defect of the whole materials based on the impurity of chemical properties throughout the material, or is it limited to localized region?
Can you that's a very valid question. Can you repeat that?
I repeat, this question was raised by Arijit Paul. Sir, in materials undergoing photoelectric effect, will the lifetime of positron be higher? I suppose there's an attached question. Can we understand the defect of the whole material based on the impurity of chemical properties throughout the material? Or is it limited to a localized region?
So I'll answer the second part of the question, because I did not get the first part of the question there. I did not understand what was the correlation between photoelectric effect and the lifetime was. But I'll first answer the second part and then probably try to make a statement towards the first part. The second part, yes, it's even though you make a doping or a defect, localized defect, you can use positron lifetime spectroscopy to look at the sample as a whole. So normally, what if you use a beam or if you use a source, you are not looking at one particular region. You will be looking at a wide region of material, and hence your information is actually averaged spatially. So depth-wise, you may get a depth resolved information, but spatially there is an average, and depending upon the beam spot that you are using, that is your averaging point. Suppose you have a micrometer positron beam spot, your information is coming from micrometer, but micrometer is still very large scale when when you think about the properties of material, right? So in normally, like in my beam spot is actually 1 millimeter in diameter. So I'm getting information from 1 millimeter in diameter, and so it's even though the information, the positron is giving information at the site at which it is annihilating, the information is spatially averaged because it is getting, I'm getting from all over the region, and I should be able to understand it in terms of the defect density or impurities. Okay, defect densities or impurities contained inside the material. It is possible to do that. Now, if you change the defect density, you should be able to see a variation in both the positron lifetime, the Doppler broadening, as well as the characteristics of OJ spectra that I just talked about.
Okay, thank you, Professor. We have another question from Midun Dominic. Is it possible to determine the porosity, pore volume, and pore diameter of nanoparticles using positron lifetime spectroscopy?
That is an excellent question. I hope it is Midun from our college. So Midun is a very good friend, Midun. So yes, you can determine the pore volume, the pore diameter, the interconnectedness of the pores of the porous material using positron lifetime, because the volume of the pore defines how much time the positron lives inside that material, and hence as your pore volume increases, your lifetime changes, and depending upon your lifetime, you can not only see the volume, you can also actually look at how interconnected those pores are, which is a very important property for membranes, which is used for all kind of applications, like for water purification or for separation and things like that. It is very important that the pores are interconnected, and presently the techniques like nitrogen adsorption and things like that are not that powerful in looking at the interconnectedness as well as the pore volume of the structure, but positron lifetime is actually a much more powerful tool to do that.
Suppose it won't be a problem if I take one or two questions more, please?
No problem.
Yeah, we have another question from Mr. J.M. Raj. How the detector distinguishes between 1.28 MeV and 511 keV gamma signal?
Oh, that's an excellent question. That's an experimentalist right there. So what do we do? What we do is actually the detector actually detects all the gamma ray energies, okay? And then the detector pulse height is directly proportional to the energy of the gamma, the energy that the gamma ray deposited into the detector. So a 511 keV gamma ray deposits a different energy than a 1.28 MeV gamma ray. Okay, so you can assume 1.28 MeV gamma ray deposits more energy than a 511 keV gamma ray in a detector of the same volume, if you keep two detectors of the same volume. So the signal which comes out of the detector, say if it is you are measuring the pulse height or say amplitude of the pulse in voltages, say for example if 511 produces a pulse height of 1 volt, then 1280 or 1.28 MeV would be producing a pulse height of 2.4, 2.5 volt, right? Because 1.28 divided by 511 is approximately 2.5 times. So if 511 produces a pulse of 1 volt, 1.28 produces a pulse of 2.5 volt. And what we do is we actually keep something called an SEA, which is called a single channel analyzer, which is a window which says, okay, look at only the pulses within 1 plus or minus say 0.1 volt, and look at, for the other detector we'll keep another window and say look at only pulses which is coming at 2.5 plus or minus 0.1 volt, and that way we can distinguish or set a detector to detect 511 keV gamma ray and a 1.28 MeV gamma ray.
Okay, we have again one more question from same participant, J.M. Raj. What information positron can give in biological samples?
Oh, that's an excellent question. Actually, there is a lot of studies right now in using. So, in my slide, I showed you something called positronium, right? So, positronium is a bound state of positron and an electron, something similar to an hydrogen atom. And in a biological sample where the free volume is very large, when I say free volume, where these open spaces is large, yeah, the positron actually most likely undergo a transition into a positronium state, okay, bound positron electron state. And positronium actually decays very differently from a positron. Positronium can decay via two methodologies. It has an orthopositronium decay and a parapositronium decay, which is the orthopositronium decay is more valid, and it undergoes a decay via 3 gamma annihilation, not 2. And this orthopositronium decay actually gives you the free volume information inside a material. And so that is one information that you get from by doing positron lifetime spectroscopy. People are actually trying to see, there is a group in Poland who are actually trying to correlate this positronium lifetime, not positron lifetime, positronium lifetime to the the cancerous nature of the tissue, if a particular tissue is cancerous or not. And they're trying to see if through positronium lifetime can you predict whether a tissue is cancerous or not. Okay, so they want to combine it to something called positron emission tomography. Positron emission tomography is widely used to scan cancerous tissues. But they also want to see whether this extra information can be used to see what is the level, what is in what stage of cancer you are in, and based on that you can decide what is the kind of medication to be given. And that is one information, okay, free volume information. Second information is the one which I showed you, is that positron itself can result in certain damage. Say, for example, it can create hole and it can result in the emission of these low energy electrons. These low energy electrons can result in DNA strand break. And that's a very important part. This DNA strand break can lead to further mutations, which can lead to bad things happening. And so you need to understand how positron interacts with biological samples in order to use it for say therapeutic purposes or for the study of other biological samples.
We have one question from Basuraj. He's from Ireland. He's a postdoc in Ireland.
Okay.
And he has mentioned it's an excellent presentation. And could surface cracks be detected in, excuse me.
Oh, surface cracks?
Yeah, I'll repeat it. It could be detected in built infrastructure using positron emission tomography.
Positron emission tomography.
Positron emission tomography. Surface cracks.
Yeah, it can be. So when you say crack, okay, it depends on the dimension of the crack that you're pointing to. Right? So if it is too large a crack, you will not basically see a difference there, because positron will just go into the surface. So if you have a crack, this is a crack, positron will just go into this surface region, and you keep getting the information from the surface. But positrons are being used for non-destructive testing. That's a big part of it. If you are interested in non-destructive technique, positrons can look at dislocation lines and dislocation movement in a material. Okay, so basically positron is a technique which you should use before your material cracks. Okay, because if it is cracking, then your material has failed. So you should use the positron before it cracks. When your defect is at as small as a dislocation line or as small as a monovatus. At that point, if you can detect your damage, then you can take mitigation steps to avoid that. Or you can say, okay, this material is defective, this is going down the failure stage, and I should replace this material. That kind of non-destructive evaluation can be done using positron. But on a crack, when I say, again, it depends on the dimensions of the crack. Even if it is a micrometer crack, positrons will not be able to tell you a difference there.
Okay, so maybe we are just reaching the end of the session, so we cannot, since we are already running late. So it was really amazing. Thank you very much, Professor, for presenting this wonderful topic in a very simple way. And I'm sure that we have a lot of MSc students and the research aspirants are attending this wonderful session, and they will be inspired to take up material science as their research in the future career. Anyway, thank you very much.
Thanks a lot, Dr. Pius, and especially Robbie, for giving me this opportunity. Sorry if my sound cracked and if I looked a little sleepy.
That was fine. That was excellent.
Sleepy, okay. But because it's 5 a.m. in the year.
Yeah, we understand.
So kindly bear with that. If I had made many mistakes, it's all mine. So please keep your.
No, there was no mistake. There was no mistake.
Dr. Pius, and probably he can forward it to me. Thanks a lot.
Sure. It was really amazing. So the thing was, it was a little lengthy because you have such a good, wonderful results, and I understand that this will be very useful for many of the students. So it was really amazing and excellent talk. Thank you very much, Varghese. And now at this point, I invite Madam Reba Chakravarti to propose a vote of thanks. Madam Reba Chakravarti.
Am I audible?
Yes, yes, please.
Okay. This is my proud privilege to propose the vote of thanks to one and all present here. There's a saying we all know that coming together is the beginning, keeping together is progress, and working together is success. Today, Spark of Sacred Heart College, Tewara, Kochi, and Department of Zoology of Holy Cross College, Agartala, has virtually proved it. Therefore, at the very onset, I would like to thank the God Almighty for helping us to join hands together to fulfill the mission of Government of India, which is Ek Bharat, Shrestha Bharat. Two colleges, namely Sacred Heart College of Kochi and Holy Cross College of Agartala, Tripura, collaborating for such academic program is a step towards achieving the mission. I, on behalf of the colleges, like to thank the principal of Sacred Heart College, Dr. Father Prasant, and Dr. Father Benny of Holy Cross College for encouraging this joint venture. Without their support and consent, this would not be possible, we all know. Thank you, Dr. Prasant, and thank you, Dr. Father Benny. I want to thank our Vice Principal, Father Shaji, for his prayerful support to bring this venture to a platform where we could gather together and we could begin and complete it very successfully. Well, this event would not have been possible today if Dr. Varghese of the Department of Physics, University of Texas, did not give his consent to speak on this occasion. We are indeed very, very thankful to him for giving his valuable time at this odd hour, which is in USA at this moment. We are in a comfortable time, we know, but for him it is probably early morning, and he had been tirelessly speaking and giving his best to make us understand the topic, that is matter, studying matter with antimatter. And frankly speaking, I myself I have benefited a lot, because I did not know anything about positron as such. But today, after listening to Dr. Varghese, I have got to understand its importance, and especially its importance in biological sciences, because I'm a faculty from biological sciences. My thanks are due to IQAC coordinators Dr. K.M. Johnson of Sacred Heart College and Dr. Pankaj Chakravarti of Holy Cross College for strengthening this bond by their support and encouragement. A special thanks to Dr. Roby Cherian, Mr. Biju, and Dr. Matthew George of Sacred Heart College, and Jinesh Augustine of Holy Cross College, who are instrumental in technical aspects of this event. I also thank my colleagues Dr. Rumki Nath, Dr. Animesh Dey, and Dr. S.K. Jamatia of the Zoology Department of Holy Cross College for their suggestions and, most importantly, their cooperations. Special thanks are due to students' representatives, namely Blesson and Paya. I understand Blesson designed the second page of the brochure, and both of them worked tirelessly to rectify all the corrections that we suggested. I will fail in my duty if I do not thank in person Dr. Pius Augustine, who came as an angel to extend his helping hand to make this dream come true. Without Dr. Pius Augustine of Sacred Heart College, who is always a very dynamic personality, this venture would not be possible. I'm indebted to Dr. Pius Augustine personally for making this collaboration happen in a very befitting manner. For me, it was an effortless venture because Dr. Pius Augustine shouldered the entire responsibility. I'm encouraged by his enthusiasm, and now that the ball is set on rolling, I understand the coming events will be much easier. Sincere thanks to you, Dr. Pius, for being my guiding partner. All said and done, if I do not thank my student participants from my task will remain incomplete. After all, this venture and those pipelined for future are all for the benefit of the students, as they are the ambassadors of New India and Future India and global world. In the present academic scenario, interdisciplinary approach is what we target at. Therefore, bioscience and physical science collaboration is an interdisciplinary approach to trigger the scientific aptitude of the students. We feel indeed encouraged by their presence, and we hope that they will continue to support us by their presence in future too. With these few words, I would like to conclude thanking all those who are present in this webinar. Thank you very much. And let me tell you, I personally have been enlightened a lot. Thanks a ton. Thank you very much.
Thank you, Madam Reba, for your wonderful words. So now we come to the end of this session. Kindly submit your feedback, and if you have further response, extended response, please send email. And we'll be having more activities shortly. And next 24th, we have got a second session that is on a computer-based program, and we will be letting you know. So most other activities are also cultural and other scientific collaboration and related activities will be coming up, and we'll be giving you the information in time. So kindly support us. Thank you very much. So we stop here. Thank you.
सारे जहां से अच्छा दोस्ता हमारा हम बुलबुल हैं ये गुलशन हमारा हमारा सारे जहां से अच्छा दोस्ता हमारा पर्वत वो सबसे ऊंचा साया आसमां का वो संतरी हमारा वो पासबा हमारा हमारा सारे जहां से अच्छा मज़हब नहीं सिखाता आपस में बैर रखना हिंदी है हम हिंदी है हम हिंदी है हम वतन है हिंदुस्ता हमारा हमारा सारे जहां से अच्छा कुछ बात है कि हस्ती मिटती नहीं हमारी सदियों रहा है दुश्मन दौरे ज़मा हमारा हमारा सारे जहां से अच्छा हिंदुस्ता हमारा
So thank you all. We stop for the day. Thank you.